Another common method of proof is proof by contradiction. Now, it's a strange thing to say because mathematicians are very logical people, very structured. Mathematics is about finding truth and what we know to hold. But contradiction, or proof by contradiction, starts by assuming something to be true, which I don't think is true. So if I want to prove that something is untrue, I say, well, let's suspend disbelief, let's pretend it's true, let's follow through the logical arguments that said if this were true, then what do I get to? And then if I reach a statement which is definitely a contradiction, a sort of P implies not P, that if P is true, P is also not true, well, that can't be right. So if my logical argument is correct at every step, the only part of it that can be wrong is the original assumption. So I say the original assumption is definitely not true, so I have proven the negation of the original assumption. So it's very strange to begin a proof based on something which I think is untrue by taking that, at least initially, to be true. Before we get to an example of proof by contradiction, I just want us to cast our minds back much earlier in our mathematical education and mathematical careers to the definition of a prime number. Now, a prime number is just an integer greater than 1, which is divisible only by 1 in itself. Every integer is divisible by 1, every integer is divisible by itself, but there's no others. Now, if I write that in logical notation, it can look a bit messy, but what it's saying is that if I have an n belonging to z, so n being a member of the set of integers, n is an integer and n is prime, that's true if and only if s does not divide n. Notice the division sign crossed out. S does not divide n for all s that I can pick from, let me just talk this through, z plus without 1 and n. So z plus is the set of positive integers. So if I take the set of positive integers, I cut out the element 1 and I cut out the element n, then all other positive integers, not 1 and not n, all of those other ones do not divide n. And this also gives us a nice bit of practice and revision of proof by contrapositive. And I will prove that all prime numbers larger than 2 are odd. So rather than proving that the statement n is prime and n is greater than 2 tells us that 2 does not divide n, I'm going to negate both sides of that statement and hence reverse the direction of implication to get the contrapositive. So the negation of 2 does not divide n is 2 divides n, and the negation of n is prime and n is greater than 2 is simply not n is prime and n is greater than 2. So now that's fairly easy to prove, since the left-hand side tells me that 2 divides n. So 2 divides n tells me that there's another integer s such that 2s equals n. So n is divisible by 2 and s, so I know that it's not prime. We can write out the list of primes, and you've probably seen this maybe on a poster on the wall of a high school mathematics classroom: 2, 3, 5, 7, 11, 13, 17, 19. As we proved on the previous slide, larger than 2, there will not be any even numbered primes. And we can see, if I write them all out, that they become less and less frequent. The top few rows have many more, and so they're fewer and further between. But it was an open question for, well, relatively early in mathematical history. Was there a finite number of primes? Would I run out of primes? Or would they keep going on and there'd be more and more and more bigger and bigger primes? So I'm going to prove that there's infinitely many prime numbers by contradiction. So the way I would prove that there's infinitely many different prime numbers is by assuming that there isn't, and then showing that that statement leads to a contradiction. Now, when I say I'm going to do this, I'm not. I'm going to steal the argument credited to Euclid. So I'm less than 2,500 years out of date here. And Euclid looks suitably unimpressed with me. Anyway, as we do with proof by contradiction, we start by assuming the thing that we're actually trying to disprove. And here, that is that there could be a finite list containing all the different prime numbers. So we start by assuming that there is some probably very large list, P1, P2, P3, and so on, up to Pn, and that any number not in that list is not prime. So if these were in order, P1 would be the first prime number, 2, P2 would be the second prime number, 3, P3 would be the third prime number, 5, and Pn would be the largest prime number, the nth largest for some n. We now consider this new number, which is made up by multiplying all of the primes that we know, which we are assuming is all primes. So we multiply all of these primes together and add 1. That's going to be a very large number. Now at this stage, I don't know what its divisors are. I don't know which integers divide into this new value n. Although we don't know which numbers do divide n, we definitely know which numbers don't, and that is critical here. Critically, none of P1, P2, ... up to Pn divide n, because by definition, our new number n, capital N, is one larger than a multiple of all of these primes. So if I divide by any of these primes, I get a remainder. So it's not divisible by any of the prime numbers. So if it's not divisible by any of the prime numbers, its set of divisors must be multiples of other primes. But the problem here is there are no other primes. I assumed that P1 up to Pn was all of the primes, and now I've shown that my new number n has to have factors which divide it, possibly just itself and 1, possibly other factors, but it has to have values which divide it, which are not multiples of the primes, so must be multiples of other primes. So when I assume that I've got all of the primes, I demonstrate that I can always find something which must be made up of multiples of other primes. So I've contradicted the idea that there are no other primes, so that means that my initial assumption that I could ever write down a list of all the primes is wrong, and so there is no finite list of all primes. There's infinitely many. Thank you, Euclid.